Hello, everybody, and welcome, or for many of you, welcome back to KETIV Virtual Academy. I'm Tyler Hart. I'm with the marketing team involved in running these weekly training and thought leadership sessions. And today's topic is designing space-ready electronics using Ansys. Your expert today is Graham Stevens, application engineer here at KETIV. Graham will introduce himself in a second, but in the meantime, if you have questions during the session, please send them to the Q&A at the bottom of your screen. These are recorded and available on ketiv.com if you'd like to review the recordings, or they're available on our YouTube channel. And as far as some upcoming events, we do have next week's KVA is optimizing configuration, pricing, and quoting strategy for maximum impact. That's the sales configuration one. And then the week after that is managing change with Vault Eco Routings. It's also worth mentioning that we have some special events outside of KVA coming up. April 17th is a sales configuration live webinar with Spectrum Industries. And then the week after that is actually in person in San Jose, California. If you can make the trip, it's with distinguished engineer Larry Williams from Ansys. Very interesting session that will be. So to attend these sessions or others, go to ketiv.com/manufacturing-leaders-exchange or visit KETIV Virtual Academy. Without further ado, I'll pass things over to Graham to kick us off. Thanks for being here, Graham.
Sure. Thanks, Tyler. Hi, I'm Graham Stevens here from KETIV, application engineer focused on Ansys products, especially high frequency and low frequency electronic applications, as well as optics. And today I'm doing a webinar on space environment electronics. So this is the workflows associated with how do we get our electronic PCB assemblies and electronic parts ready for space. So this is very much focused on that space environment. And so when we think about space and the challenges that space presents for electronics, we have sort of a laundry list of different kinds of challenges, of types of analyses that we would want to run. And this really gets important because out in outer space, if something goes wrong or if an error has been made, you're sort of done. And so it's very high risk and it's also very expensive. So launch costs are quite high, in the millions of dollars range. And so you want to make sure before it gets there that you've done as much simulating as possible so that you don't have any errors, don't have any issues when the product is actually performing in the field. And so with that additional sort of risk and cost challenges, these are some of the additional environmental factors that you need to take into account and think about when it comes to electronics for space. So the first challenge is launch vibration. When we do a launch and my electronic box is on a rocket, there's basically a dynamic explosive charge that's lit underneath the rocket, and then obviously zooms forward, and there's a shock wave and associated sort of vibration dynamics, and so we need to make sure that our electronics will survive that, will thrive, that the vibration isolation that I might have put in place works. And so to solve that challenge, you would use LS-DYNA or Ansys Mechanical. And then also in space is ionization and radiation. So we have in outer space, you have gamma rays, you have rays from the sun, all sorts of different radiation sources. And those radiation can penetrate through the shielding that might be existent on the aircraft, on the spacecraft, and then affect electronics. So we'll be talking some more about how we can mitigate that and examine that with a program called Charge Plus. In addition, in the reaches of outer space where you have the electronics are operating in a vacuum, you have electrostatic discharge and arcing phenomenon that can be it changed, I guess, is probably the best way to put it. When we're in air, we have Paschen law and arcing happening with air versus vacuum, which is slightly different. And so you need to account for that. And also under vacuum, you have outgassing that might happen. And so we may want to examine our materials for outgassing. Then we have temperature extremes in outer space. We have a big issue is how do I cool my electronics? How do I cool my assemblies? In outer space, you don't have any air, so there's no convection possible unless you have maybe a heat pipe inside the heat pipe. And or diffusion in terms of conduction, because there's no place for the heat to go. And so you're left with radiation to be able to cool things. And so we have to account for that effectively. And then in outer space, we have some serious high temperature, both extremes, plus or minus 200 degrees at the lunar surface, a 300 degree C temperature delta from when my satellite's facing the sun versus when it's blocked by the Earth. And then pretty high temperature gradients when I'm doing that switch. All of a sudden, it goes from minus 200 to plus 200 very quickly. And so we need to analyze, can my electronic assemblies handle those sorts of temperature extremes? And then finally, because of the high risk, the cost, and the difficulty of fixing things if something goes wrong, you want to kind of be much more proactive with regards to reliability. In space, in the vacuum of space, you have the potential for spontaneous growth of tin whiskers as one potential additional reliability mechanism, but your overall reliability is also something of high interest in terms of addressing for space. And Sherlock is an application here at Ansys that can help with that. So with that introduction, we'll be kind of just jumping into each of these individual areas to show you some of the programs and workflows that you would dive into. And as I'm kind of focused here on electronics, I'll be sort of fingering some of these applications and saying, here's some further resources if you want to go into say LS Dyno or mechanical, which is certainly not in the electronics purview. But I wanted to give everybody sort of a jump off point for if I need to consider this sort of stuff, what do I need? How do I do it? Where do I go from here? And so when we think about space charging simulations or doing these sorts of space simulations, as I said, the risk is very high. This is one example of Telesat Canada's Anik E satellite, where two satellites began spinning out of control and you lost $100 million. And spacecraft charging caused that failure. It was an ESD to gyroscopic guidance system failure. And so you have to sort of, when you have these aircraft or these spacecraft out in outer space, you have to start thinking about charging because it can really impact your operations, sometimes in odd ways, which you might not have thought about. And just some examples of our budding space industry. We have Rocket Lab, which has been doing launches since 2017. Of the 4 out of 45 launches that were failures, a bunch of them were electrical related, whether it's an electrical connection or an igniter fault or an arc. Electrical failures tends to be where it's at in terms of outer space and issues. What's interesting though is SpaceX, one of who's done large numbers of launches and had a number of spectacular failures. It uses Ansys and an iterative design approach to fail fast and fail often. You can sort of see here's this launch tube, and they had a number of failures for that, but then eventually they got to being able to land the rocket booster back on a C platform effectively, which then of course cuts your launch costs dramatically because I can reuse my rocket boosters. And with their use of Ansys, I'm not sure we can sort of say correlation is effect here, but given their use of Ansys, they have gotten to a pretty high success rate in terms of their rockets over time, and only few of them are electrical failures. So we can certainly say that Ansys has helped as they've gone forward. And one of the other reasons you want to do simulation, particularly for space applications, is that with that high risk and cost, it costs a lot more to do design changes later in the design cycle. So if I'm in production or testing, or the product is out in outer space, it's very hard to fix and change. Recalls for space don't really work terribly well. And so you want to do a lot more upfront design and simulation and risk mitigation, as much as possible to avoid anything happening in these later stages, whether that's due to manufacturing tolerance variation or otherwise. But it's very important to do simulation early to catch those mistakes early, where it's much easier to fix them when you know about them early. So when we think about kind of launch dynamics, and how do we tell whether our electronic board is going to survive launch, typically users will start with Ansys Mechanical, and there's some dynamic analyses you would start with. The first is sort of a modal analysis to see what the natural frequencies of the structures are. And then you might do a random vibration analysis. And in particular for launch, you would also jump to something called a response spectrum analysis. And this is where I have a shock wave or a random or a time-dependent loading condition. And I want to, here we have an acceleration pulse. And then I want to see what's my maximum response of my structure to that pulse to make sure it can withstand that shock loading. And typically this is sort of where people stop in terms of this sort of launch analysis. But if you want to examine that further in terms of maybe examining what is this acceleration curve actually come from or derive from, there's also a module called LS-DYNA, which focuses using explicit methods on stuff that happens very, very quickly. So any analyses sort of less than a second, whether it's drop or impact or ballistic or hypervelocity, you can analyze that sort of split second by split second using LS-DYNA. And we can sort of see here's sort of a Whipple shield impact test where we have an aluminum BB kind of hitting the aluminum to see what that effect that has. So we can also look at foam debris or dust clouds kind of potentially impacting the rocket or operations as you go forward as well. So as I said, this is part of the mechanical suite, which is out of my purview, but we'll give you some links at the end to sort of jump into that arena if you'd like, and we'll go from there. So then when it comes to surface charging, I mentioned how we have radiation space constantly hitting the satellite, hitting the vehicle, and there's a whole bunch of additional physics that happens. So we have sunlight, we have incident ions, we might have incident electrons. Each of those can then create photo emission or secondary electrons from dielectrics or potentially from the metals. So we have a whole host of different phenomenon here that can happen. We can get surface charging, and as I mentioned before, if you get penetration of this radiation into the spacecraft, you can get volumetric charging or phenomena happening as well in terms of ionization. So there's a number of different things we can do on the electronic side around this. First of all, is you can model what that internal charging of the bulk material might be. So with the high energy particles penetrating deep, we have currents that can be induced on the conductors and dielectrics. And then you might get into an electrostatic discharge situation. There's something called radiation hardening, where you look at monitoring that flux and radiation dose before and after interactions to just verify that the shielding you have in place is going to be effective for the amount of time you're operating in space. And then we can model directly that electrostatic discharge, whether it's breakdown voltage in the plastics or breakdown voltage between conductors. We can look at arcs, we can look at ESD as well. When we're thinking about the inputs for that kind of analysis, we can gather that MRS file for mission STK SEET within Ansys's STK module. We can grab what the high energy particle spectrum over time for a particular mission might be, and then feed that forward into the next module in Ansys that I'll introduce, Charge Plus, to take those plasma parameters versus time as an input, and then start computing surface or internal charging to see how our shielding is performing. And so just wanted you to be aware that you might be given this specification in terms of the high energy particle spectrum over time. But if you don't have it, you can get it from STK. And then Charge Plus is a finite difference time domain full 3D solver, which has a nonlinear air chemistry module built into it. And this is what we're using to do this kind of solving relative to electrostatic surface charging, relative to internal charging, Monte Carlo transport of energetic particles and radiation hardening with the bulk materials, looking at particle and cell models to track low energy charged particles and collisions, and finally fluids if we're looking at dense plasmas and coupling. So all of these are part of the Ansys Charge Plus package. It's fully integrated into Ansys Discovery or Spaceplane, as some of you may know it. So within that package, you bring in your 3D models and geometry, and then it's an additional menu or two as part of Discovery to model, set up the boundary conditions and do the modeling for Ansys Charge Plus. And so these are just some of the outputs that we can get. We can look at surface charge monitoring of the surrounding fields. We can look at in the lunar environment, if you have dust and triboelectrification happening, we can examine that. We can look at the internal charging of a sub-D connector is depicted here. So again, we're in Discovery, we brought in our connector, and now we're grabbing the data from STK. We're then doing an internal charging on the dielectric, meshing it, as you can see the mesh here. We're looking at the electron tracks that might be present in terms of exposure, and then looking at the results in terms of what sort of E fields are present. And it's a little hard to see right here in the right-hand corner here, but we can take a look at through the connector, what are the fields and how do they, what's actually happening. And here's some additional results here, looking at total dose and electric field magnitudes as a post-processing, and then do the same sort of thing in terms of radiation hardening, where we have a 1 millimeter aluminum shield. We're shielding this electronics box. We're putting it through the radiation belt, and now we want to figure out, well, how well is that shielding working? We can go from the spectra to the dose on the silicon in the the dielectric layers on the chip to understand what the dose is. You can sort of see here how we have different types of radiation and their penetration through different materials, and then keep track of flux density in 3D for this simulation. You can sort of see how we're looking at an actual animation of what the flux density changes over time, and really understand that. And then in the when we're thinking about arcing and electrostatic discharge, Ansys Charge Plus uses a full wave FEM solver and calculates the probability of electronic breakdown for each element using this equation here, essentially, where we have, intrinsic breakdown, streamer avalanche, thermal, erosion, electrochemical, kind of, and a time curve. So this is just a model of breakdown that's used. And then we can do ESD testing on electronics enclosures, where we look at the dielectric properties that affect voltage breakdown, explicitly simulate the ESD propagation and demonstrate the location of issues. So you can see here, we do where are we seeing electrostatic discharge happening in our PCB? So all of this type of analysis is possible. And this is just sort of a cool animation for the day, where we're looking at the actual voltage excitation and the current pulses within a PCB board. So this is also feasible in this tool. So, and then with PCBs, we can also look at flashovers and arcing currents. We can see this animation here is showing the electric current and where you might have a flashover here, and verify and validate that we're not going to have issues with arcing as we're looking at things. And then when we're starting to think about outgassing, we might want to look at material properties. Ansys Granta is an advanced is a materials database with a number of properties associated with thermal conductivity and some of these other analyses we've been talking about, as well as for high frequency and low frequency applications. So please do keep that in mind relative to designing your products for reduced outgassing. And then for extreme temperatures, again, this is not as much in the electronics realm, except for ice packs. So for this particular slide, I just wanted to spend some time and go over when you would use what package for what types of tasks. So in general, when we're talking about extreme temperatures, Fluent is sort of a good place to start. IcePack in particular, which uses the same underlying CFD engine as Fluent, is great for PCB enclosures. But when we're in outer space, of course, we're only talking about thermal radiation for the most part. So I emphasized here what sort of conduction or convection modeling capability is present for each of these packages, as well as what kind of thermal radiation model the package is used for. So in particular, mechanical is a little bit limited. It has a surface-to-surface radiation model, which is a little bit less accurate than the Monte Carlo or some of these other thermal radiation models within Fluent. And then if we want to get really accurate, we should probably jump to an optical ray tracing model to do a very detailed ray tracing, either in Zmax or SPIOS, depending on whether you're looking at sequential optical simulations, kind of where's the light going through a particular device, like lens to lens, lens surface to lens surface to lens surface, or if I'm doing something non-sequential where I'm just wanting to see how does stuff bounce off of surfaces and what's the output through that design. And then finally, LS-DYNA has only heat transfer coefficient capabilities in terms of its thermal radiation. But if you are doing some sort of split-second transient, that is where this analysis shines relative to doing extreme temperature analyses. So right after launch might be a good time to do an LS-DYNA analysis. And then in space applications in particular, Thermal Desktop has a very high usage, and it's more at the system level. So there's a Monte Carlo thermal radiation model embedded in it, but it's more of a system level analysis. So if I have a a satellite system that I'm looking at analyzing, you might start at the system level here with Thermal Desktop, or at the mission level with SDK and AGI. And then if the analysis at the system level says, oh yeah, I need to start looking in more closer detail at this particular aspect of the satellite, of this particular component, then I might go to more of a detailed component model, either in Fluent or IcePack. And of course, mechanical can help you with looking at thermal stress and strain. So we may have some multiphysics here where we do a temperature analysis from one of these thermal radiation models, and then send that temperature distribution to mechanical to then look at the thermal stress and strain that's produced. And we can even take that thermal stress and strain and then output it back to, say, the optics to see how it impacts optics, or output it back to the RF antenna and see how it impacts my RF antenna performance. So those are some additional multiphysics that might be present. And of course, when we're talking about temperature extremes, one of the key factors here is making sure that we have material properties well described as how they change over the full temperature range. So if I'm going from -200C to +200C, I might need to see how the electrical conductivity changes of the copper changes over that entire field, over the entire temperature range, so that I can really get the impact of joule heating nailed down well. And so you have additional material property requirements that you might not see on a standard spec sheet that you might be able to use Granta for. And then lastly, I wanted to mention PCB reliability for power electronics. There's a package called Sherlock within the Ansys mechanical realm that starts with a database of a component database on your PCB board, all the resistors, all the different chips, where it has listed for it are basically anything, properties associated with the reliability. And by just getting a bill of materials for your PCB board, I can get relatively quickly, and the layout, I can get a very rough, not rough, but just a good estimate of mean time between failure for each individual component on the board, which then allows you to estimate the mean time between failure for the entire board. And then I might finger different analyses and say, I want to dial in on doing an electrical simulation to get a little bit more accurate on the current that's actually impacting this aspect of the board or not, or look at the flow fields and temperatures, or look at shock and vibration analysis. And so then you can do those FEA simulations and integrate the information from those back into Sherlock and get more accurate estimates of total reliability. So just wanted to be aware of this package and its capabilities. And then in particular for our nickel filaments that are growing in the vacuum, there's a specific conductive anodic filament electrolytic capacitor wear-out analysis that's part of the Sherlock tool that might be of interest. But of course, as we're diving into reliability, some of the highest issues with the reliability concern fatigue and thermal and vibration. And so you may want to do those analyses as well to make sure we're having our boards work well before they ever get to space, so they will work well in space. And with that, I will open the field up for questions. Wondering if anybody has any questions.
Thank you so much, Graham. That was fantastic, as usual. We don't have any questions yet. Please feel free to get into the Q&A if you do have questions for Graham. But this will be recorded on KETIV.com under our KETIV Virtual Academy section. Otherwise, it is always on our YouTube channel. And yeah, Graham, I'll pass it back off to you to close us out.
Sure. So I just wanted to say in conclusion, Ansys can solve your space-related electronic challenges before you even put your electronic components into space. And if you're looking for additional support and where do I go to next? The Ansys Learning Hub is a repository of online courses to help you learn both the capabilities, but also learn how to use each of these individual software components. So Ansys Mechanical, there's a link here, LS Dyna Learning Room here, Charge Plus, Sherlock. So these are sort of where you would go to get started on this. And as you're going through that material, or if you have a particular task, you're not sure which tool to use or how am I going to do this, please do reach out to support@ketiv.com or call us here. And then there's some other resources here, both the Ansys how-to YouTube channel, there are some webinars, and then the Ansys Innovation Space, again, has some public courses available for use. So I just wanted to be aware of all these resources. In addition, if your company does not have the capacity for doing simulations, KETIV provides simulation services in these three areas: mechanical, fluid, and electronics. We're happy to do it for you. We're happy to do it, teach you how to do it, or have you do it 100% or anywhere in between in terms of training, getting up to speed. So please be aware that we do this and that we're happy to help in whatever capacity makes sense. And then I'm finished.
Awesome. Thanks so much, Graham. Thanks, everybody.